Everybody. Respected Chief Guest and Speaker, Dr. Mahendra V. Professor, we are welcoming you, sir, for this August gathering and educational webinar.
Thank you, sir.
We are highly thankful to you for accepting our invitation. In near future also, we are expecting the same cooperation in a efficient way. We will make the arrangements next time, as and when situation come back to a normal situation. Definitely, we will conduct a 3-day workshop before December or January. This is my promise, and
Sure.
we want to learn so many things from you. And I request on behalf of our faculty and family of ECE department to educate and to benefit with your words and speech, sir. And regarding our college, Matrusri Engineering College was established in 2011, 9+ years going on as on today. 5 batches passed out in all departments successfully, and more than 85% students placed from 85 to 92% EC department especially, and majority 22% out of which were settled in higher studies. After completion of higher studies, they came back, and here two startups also initiated in our college, our alumni, and the Department of ECE established in 2011 with 60 as intake, and later on next year it was enhanced to 120, sir. And from since its inception, the Department of ECE is very proud enough to say to conduct workshops, seminars, and other activities, including industry visits, to impart training to the students more and more actively. And the laboratories are established according to OU curriculum. And 2019 January, we were qualified for 3 years a National Board of Accreditation with 70% outcome. And our students are well established in various companies, and the faculty members are 21 faculty members are available, out of which myself, Sushant Babu, and one more professor is joining within short time. 4 associate professors, 3 professors, and remaining all are assistant professors. As on today, 6 PhD degree holders are available in VLSI, electromagnetic field theory, and antenna myself, and wireless sensor networks and communication, mobile cellular, Sushant Babu, and one more VLSI professor is joining within short time. And already embedded system professor Gopal Manigar also there, due to some other reasons is at home now. Anyway, now the departmental activities are concerned. We are conducting conferences, workshops, seminars time to time to impart training, and 6 industry study visits we have been arranged, ISRO and Shore Center Nelluru, and local Invoice Center, and not only but also ISTRAC Bangalore 2 times, and GMRT Pune, Giant Meter Radio Telescope, and whatnot. According to the curriculum, we are trying our level best, and we had IEEE WIE professional bodies, and we are doing on that banner also to impart training. And lab assistants also we are arranging trainings, sir. Now we are in the 10th year, and 6th batch is coming out, and with this and we had a E-Entra lab 5 lakhs worth, and R&D lab also, Texas Instruments, BSNL, and embedded systems, and IIT virtual labs, or IIT Mumbai spoken tutorial, or with all these external agencies, including E&ICT Academy. Second time we are commissioned already MOU to educate our faculty not only across India. We are having nodal center, and we submitted virtual lab experiments also. So these all are the outcomes, and we are struggling to get next time NBA minimum 5 years to 6 years. That is our target, sir. This is a brief introduction. Thank you very much. Over to Mahendra V.
Thank you, sir. Thank you. very much for
Now Aruna madam will introduce a brief bio sketch of yours, sir. Please, Aruna
sure,
madam.
sir.
Now I feel honored to introduce our today's speaker, Dr. Mahendra Usha. He is working as a professor of EC department, MLRIT, Dundigal, Hyderabad. His education qualifications are he passed out the BTech from JNTU Hyderabad in 2007, MTech with a specialization in VLSI and embedded system from NIT Bhopal in 2009, and completed his PhD with a specialization in VLSI reconfigurable computing in 2016 from MNIT Bhopal. And his research interests are embedded system design through FPGA, on-chip heterogeneous architecture design, and hardware-software co-design. He's having the 11 years of working experience, and he's awarded with the Early Career Research Award for the design and development of on-chip heterogeneous multi-core platform for secure multimedia applications funded by SERB DST Government of India. And he is the nodal officer of MLRIT for Smart India Hackathon organized recently by MHRD Innovation Cell for the years 2018, 2019, and 2020. He is associate member of IETE and author membership with the Scopus and RC. His research contributions with the 3 patents and published more than 24 journals and conferences. Thank you, sir. We are welcoming you to Matrusri Engineering College for giving the webinar on programmable logic devices, architecture and its future opportunities. Thank you.
Thank you, Madam Aruna, and I thank Dr. Srinivas Garu for choosing me as a resource person for this webinar. And recently, 3 days back, I got opportunity to meet one of our student who presented their project in Smart India Hackathon in front of Prime Minister. Now, from there also I got good experience of our department. So I am privileged to deliver my webinar for the students of Matrusri Engineering College. Thank you. And now, without any delay, let us start with the webinar named as Programmable Logic Devices, where we will be understanding the architectures and the future opportunities of programmable logic devices. And myself, Dr. Mahendra, I hope already Professor Madam Aruna introduced to you. Now here let us see the outlines what we are going to discuss in this webinar. Now initially I am going to give you the background of VLSI design flow and its implementation styles, and then history of programmable logic devices, then architectures of programmable logic devices, and then the emerging programmable logic device, that is field programmable gate array architectures we will see. After that, we could see how field programmable gate array supports parallel processing, and also we could see the implementation process of digital systems on FPGA. Now, after that, I will give you an example of a digital system design, and then I will introduce you the commercial tools and devices which are available to work with, and finally, I will give you the various field programmable gate arrays released by the Xilinx company, where I am also working, and I suggest you to work on this Xilinx field programmable gate arrays. And finally, I will present you the applications and the challenges of FPGAs. Now, this complete presentation goes for 1 hour, where 15 minutes I will be presenting, and we will have more than 10 minutes for queries. Now, I hope students and faculty are the audience of this webinar, and most of you gone through the VLSI design flow. Here, I would like to stress upon the abstraction levels of VLSI design flow. Here, you could see there are 5 abstraction levels, starting from system, module, gate, circuit, and device. These are the 5 abstraction levels. One can start designing digital systems or VLSI circuits starting from system design, system to the device, that is high level to the lower level, or some can start designing the VLSI circuits starting from device to the system level. In the system, we will be dealing with the bigger systems, for example, designing of microprocessors, designing of the core process, designing of memories, all this comes under the system level. And the module level, we can design the individual modules of a larger system. In the gate level, we will develop the modules by interconnecting the logic gates. In the circuit level, we will develop the logic gates by interconnecting the circuits. At the device level, we will develop the circuits by using the transistors. Now, these are the abstraction levels. At the lower level, we will be dealing with the transistors. At the top level, we will be dealing with system. Now, one can follow either top-down approach or bottom-up approach. Top-down approach means they start designing VLSI systems from system level to the device. Some others can start from transistors to the interconnection of all the modules and then a final system. Now, these are the 5 abstraction levels what we could see. Now, let us dive deep into the abstraction levels. Now, here you could see the same abstraction levels are kept here. Now, you could see what all the devices, what you are seeing in real life falls under the system. Now, here you could see microprocessors, general purpose processors, memories, programmable logic devices, whatever is today's topic. Okay, FPGAs, these all are manufacturing of all these comes under the system level. At the module levels, we could see the designing of combinational circuits, sequential circuits, registers, all those at the module level. At the logic level, you could see the static and dynamic gate logics. The circuit level, we will be interconnecting the transistors. At the device level, we will use the layers to manufacture the more efficient devices. Now, these are the 5 abstraction levels what generally we follow in VLSI design. Now, coming to the VLSI design styles, here you could see there are 3 design styles. One is full custom, second one is semi-custom, third one is user programmable. Now, here full custom, as I shown, there are 5 abstraction levels. If one can follow these all 5 abstraction levels, one can follow all these abstract. That means if they start from the device to the system, then we can call that as full custom. That means they only developing the transistors, interconnecting the transistors as the circuits, then circuits as the gates, gates as the modules, then finally interconnection of the modules will give you system. That is what, starting from the transistor to the interconnection of the modules and then developing the complete system will comes under the full custom. That means they will be dealing with all the abstraction levels which are there in VLSI design flow. We can call that as full custom design. Next, coming to semi-custom, and here design can start from the gate level, gate abstraction levels. Now, here you could see the gate, module and system. They can deal with only 3 abstraction levels. They don't touch upon the circuit level and device level. That means they do semi-custom. That means they customize the circuit starting from the gate. Gates are interconnected to develop the modules, and modules are interconnected to develop the systems. Now, if they follow this methodology, then we can call that style as semi-custom style. And third style is user programmable device. There are off-the-shelf devices available called programmable logic devices, out of which popular one is field programmable gate array that we will be studying in the soon. Okay, in next slides. But here now these user programmable devices are also getting popular because of the products want to be released at the earliest into the market in such a way that there is more significance to the programmable logic devices. That's why today we have taken the topic of programmable logic devices to understand how these programmable logic devices help the designer to release the product quickly into the market. Now, these are the 3 design styles what we could use, but out of which full custom and semi-custom require the manufacturing industry, but user programmable device does not require any manufacturing unit at our place. Now, in this webinar, we will be focusing more on programmable logic devices. Now, let us move to the next. As I said, full custom design style is having very good performance, but it takes huge time to market. Now, whatever I have kept here in this slide, those are the drawbacks of full custom design. It's not drawback, but we need to consider them as one of the parameter which restrict us to go for full custom design style. But always full custom design style gives us efficiency in circuits. But here there are some hurdles. What we can see, that is time to market is very high and labor intensive. So we need to recruit more engineers. Designer have to put more people to work on various abstraction levels. As I said, the designer have to work in all the abstraction levels. In order to work in all the abstraction levels, there is a need of more engineers to work upon. That leads to high NRE cost. But it is more efficient of all the styles. Now, coming to the semi-custom design, here as I said, we will not touch upon the transistor as well circuit level. We will be developing the integrated circuits just by considering the logic gates. And for that, this is the sequence what we can follow, starting from the specification capturing to the high level description, where we use the Verilog HDL or VHDL to describe the behavior, and then we will convert that HDL code into the gate level logic. We can call that as gate level design. After the synthesis, we will get it. Anyway, later I will tell you what are the processes, and then we can send it for the manufacturing after the completion of the physical design process. Now here you could see half of means two abstraction levels were removed. So there would be enhancement in time to market. That is what, as compared to full custom design, there would be less time taken by the semi-custom design to release the product into the market. But this also require more NRE cost, but fairly optimized for area, power, and timings. Now, next is programmable logic devices. Now let us look at programmable logic taxonomy. From the previous slides, we can understand that the full custom device takes very huge time to market, where in semi-custom style, that time to market time got reduced. But now in the programmable logic devices, that will be further minimized. Now in this webinar, we will be going through the stages where we can understand how effectively these programmable logic devices minimize the time to market. Now here let us look at the programmable logic taxonomy. Here there are many programmable logic devices what we could see in regular our life, and here we have categorized them into two. One is factory programmable devices and field programmable devices. Factory programmable devices means there would be programming happen at the manufacturing stage, but in the field programmable devices, there is chance of programming the devices in the field where you are working. Now here, if you look at the factory programmable devices, there are two kinds of devices, that is ROM, read-only memory, and MPGA, that is mass programmable gate arrays. Now these are the factory programmable logic devices. Since this is factory programmable logic devices, which will not provide as much benefits. Why? Because as the user, we need the flexibility to change the functionality in our hand or in the field where you are working. But these two devices will not give you that benefit. That's why we market or industry is not much concentrating on the field factory programmable devices. But coming to the field programmable devices, here you could see there are three categories of field programmable devices: simple programmable logic device, complex programmable logic device, field programmable gate arrays. We can shortly we can call them as SPLD, CPLD, FECA. Now these are the three field programmable devices what is available, out of which SPLD is having four categories. Now here you could see blue color, the same blue color is extended to the bottom 4. That indicates that those 4 are the family of SPLD. That is PROM, programmable read-only memories, PLS, PAL, and GAL. Now these are the 4 programmable devices comes under the SPLD family, simple programmable logic devices. And these programmable logic devices having very less number of logic gates or have the small area to design the circuits. Because of that, we cannot extend these SPLDs for implementation of complex circuits. Now coming to the CPLD, that is complex programmable logic device, where you can find some more programmable logic areas where we can use configuration of the architecture, that is CPLD, for developing medium or less complex VLSI circuits. Now coming to the field programmable gate array, this is the programmable device introduced recently in the sense 10 years back into the market, where there are more number of programmable gate arrays are available. We can use those programmable gate arrays to design complex VLSI circuits. Now here difference between these three is only the area which is available for reprogramming. Now SPLs are having very less, I can say, in terms of 100 to 1000 logic gates are available, and with the help of that 100 to 1000 logic gates, we can develop very small VLSI circuits. But in CPLD, that we having the logic gates in terms of thousands, so that also cannot accommodate the complex systems. But FPGA will have the logic gates in terms of lakhs, so we can use the FPGAs for complex systems also. Now let us move to next, field programmable gate devices. Now here I have kept the complexity, where you could see the parameters, density, timing, cost, and vendors who supplies these devices. SPLDs are low and few hundreds of gates. As I said, we cannot use it for the complex VLSI circuits. CPLD will has low to medium logic gate, that is 500 to 1200. But in the field programmable gate array, you could see 3K to 5000K logic gates are available. We can call that as medium to high. That is why the field programmable gate arrays nowadays widely used for the complex VLSI circuits also. Now coming to the timing, we can predict the time of SPL and CPLD easily. Why? Because less number of logic gates are available, and we can predict. Here we cannot exactly find, but we can predict how much time that circuit takes if we configure the circuit on SPLD or CPLD. But that cannot be unpredictable on FPGAs. But there are certain tools which can be used to predict the time of the system which will be executed or which will be configured on field programmable gate array. Now coming to the vendors, these are the vendors. Here I kept, these are the vendors, out of which major vendors are Xilinx and Altera. These are the vendors who are developing the wide range of CPLD and FPGAs for the current scenario. Now at the end, I will explain you what are the various devices released by these companies in order to support us to work with. Now let us look at the wide category of user programmable devices. Previously we have seen the taxonomy of field programmable logic devices. Now here you could see programmable logic devices and FPGAs. These are the widely used devices. Previously whatever I have introduced, Those are the programmable logic devices which are available. But now whatever you could see on the screen, these are the programmable devices are widely used in current scenario. Now programmable logic device, read only memory, programmable logic array, that is PLA, programmable array logic. These are the devices used for small scale applications, and the field programmable gate array is used for large scale applications. Now if you look at programmable logic devices where ROM is have the problem of area efficiency. In PLA we have the problem of two-level programming that adds the delay for the circuit. Now in PAL you could see logic plane structure that grows rapidly, that indicates that if the complexity of the circuit is more, that increases the logic plane structure, right? That is based on the number of inputs, the configuration and the time delay, everything will vary if you use PAL. From this we can understand these devices are used for small scale applications and also has their own drawbacks in order to use them for the critical applications. Here critical applications in the sense where speed is most important, not only complexity. Here wherever speed is most important, there we cannot use these programmable logic devices. In where critical applications we are going to develop, there we can use the field programmable gate array. So in further topics we will be studying more on field programmable gate array. From this slide we can understand clearly that where field programmable gate array gives the benefits for both complex as well time constrained VLSI circuits. Now look at the CPLD versus FPGA. You may see here there is CPLD missed. Why? Because now here we could see only two kinds of devices, where CPLD also having the equal capability of field programmable gate arrays, but there is small difference between the CPLD and FPGA. In this slide we will be understanding what is the architectural difference between CPLD and FPGA. Now if you look at the logic, the CPLD will have AND and OR logic, but FPGAs will have the multiplexers, lookup tables and gates as logic blocks. Now register to logic ratio is small in CPLD. As I said, number of logic gates are small in CPLD, but in a field programmable gate array that is very high. Now coming to the timing is very simple, but in a field programmable gate array that is complex. Architecture variations are very small. Here large, that there are large varieties of field programmable gate arrays are available. Now programming technology used for CPLD is flash, but in FPGAs we can use SRAM, anti-fuse and flash. There are three kinds of programming technology we can use in field programmable gate arrays. Then capacity is 10K. This is approximate capacity, and here in FPGAs 2M, that is mega. Lookup tables plus RAM. RAM memory is available for programming the architectures. Now these are the architectural differences between CPL and FPGA. From this clearly we can understand that even though CPLD exhibits the same features of FPGA, because of its number of logic gates, we will not use the CPLD for complex applications. But field programmable gate array satisfy the requirements for complex applications. That's why hereafter our discussion will go on field programmable gate arrays. Now look at the ASICs and FPGAs. Now there is one more device, application specific integrated circuit and FPGAs. Now you may have the doubt that why to use field programmable gate arrays only. Why not ASIC? As I said, ASIC is either full custom VLSI circuit or semi-custom VLSI circuit. There is a need of the manufacturing unit for the ASIC, but for the FPGA that is not required. We can reprogram the architecture of the FPGA in the field where we are working. Now, if you look at the diagram, where you could see the flexibility on y-axis, performance on y-axis. Here you can see the ASIC, application specific integrated, is very efficient in terms of performance, but it restricts the flexibility. Flexibility in the sense we cannot reprogram the ASIC. But nowadays, in current scenario, we require the flexibility at the most. If there is no flexibility in the system, that system may not last for longer time in the market. Why? Because there is continuous updations are happening very quickly, and there should be a device that can adapt for those continuous updates. Now, if you look at the field programmable gate array, that has both flexibility as well performance, whereas DSP processor and ISP indicates that instruction set processors, those are our general purpose processors and the DSP processors will have more flexibility. Why? Because we use the only software programming, so they have the very high flexibility, but they restrict the performance. But here you could see field programmable gate array is the intermediate between both flexibility and performance. Now, this is the requirement of today. That's why we study more on field programmable gate arrays in our BTech subjects also, because they don't ask you to go for manufacturing the integrated circuits. They ask you to verify your logic whether it is right or wrong in the lab itself, where we can effectively use field programmable gate arrays to test the system what you have developed. That is what the flexibility, whatever system you have developed by using HDD languages, immediately we can test that system by using the FPGAs, but that is not possible through ASIC. ASIC requires manufacturing unit, and that is not available in most of the places in India. Now, these are the few comparisons of ASIC and FPGAs. Here, ASICs are having high performance, low power, but it gives low cost in high volumes. That means if you want to go for a manufacturing of the same system in terms of lakhs, then ASIC will give you the low cost. But wherein field programmable gate array is off the shelf, low development cost, short time to market, and have the reconfigurability, that is what flexibility. This gives us the rapid prototyping flexibility, but it costs very high for small volumes. Small volumes means if you want to develop 10 systems or 10 similar kind of systems, and then you can choose FPGA instead of ASIC, and FPGAs will support, but at the cost of more. That means if you want to develop 10 systems, you need to purchase 10 FPGAs. But here manufacturing of 10 ASICs is cost very high. That is what here clearly they stated, that low cost in high volumes. Whenever you go for high volumes, then only ASIC will give you low cost. But as compared to the ASIC, FPGA will give you the best cost for low volumes. Now, this is what the comparison between ASIC and FPGA. From this we can understand that ASIC is having the benefits of high performance and also low cost in high volumes, but FPGA is off the chip, off the shelf device, where we can develop the system rapidly, but gives the poor performance as compared to the ASIC at moderate cost. Now let us look at the history of field programmable gate array. From this we have understood clearly that field programmable gate array is the device which gives us the more benefits as compared to small scale programmable logic devices, TPLDs and ASICs. So hereafter we will concentrate more on field programmable gate array architectures. Now, first FPGA was released in 1985 by the Xilinx company. Before that, there was the FPGAs were released, but commercially available FPGA is made in 1985, and these FPGAs will have 2D array of logic blocks and flip-flops with programmable interconnections. Now let us look at the architecture. Now this is the architecture of field programmable gate array. Now you could see here at the right hand side in the figure, you could see the FPGA architecture will has majorly 3 functional blocks. First one is configurable logic block, second one is input output blocks, third one is block RAM. Now these are the major resources in FPGA architecture. Now here you could see configurable logic blocks are kept in the 2D array. That is what in previous slide I kept. Now this is a 2D array having many configurable logic blocks which supports the programmability. Now you could see here the configurable logic blocks consist of RAM based lookup tables to interconnect and implement logic. Now input output blocks are used for interconnecting IO pins with internal logics. Now here configurable logic blocks are the internal logic where we can configure our logic or system logic with the help of the lookup table. Now that logic can be interconnected through the external devices through input output pins. Now here input output pins can act as the control flow pins between internal logic and external interconnections. Now block RAM is used for storing large amount of data inside the FPGAs. Now for configuring the FPGA, we have to store the bit file. Now this block RAM acts as the storage element to store the bit file and then configure the entire FPGA as per the functionality of the system. Now apart from these major function blocks, there will be function blocks called multipliers. In some of the FPGAs we can call these multipliers as DSP, digital signal processing blocks, to support multiplication operation, and also digital clock manager that manipulates the clock signals inside the FPGA. Since in the FPGA there will be many function blocks will be configured, and those function blocks will run at different speeds. In order to generate the clock with the different speeds, we can use digital clock manager. This digital clock manager manipulates the clock signals, that indicates that manipulates the speed of the clock signals based on the functions requirement. Now I hope you understood what are the major function blocks exist in field programmable gate array. Now here you could see majorly CLBs, that is configurable logic blocks, where we can configure our logic. Then input output blocks supports interconnection of internal logic to the external world. Block RAM supports storage of large data inside the FPGAs. And multiplier blocks and digital clock managers will support the functionality of CLBs. Now let's look at the features and specifications in FPGA. Now as I said, there is CLB. Now here you could see only one block CLB. Now you could see here what are the internal functional blocks in that CLB block. Now the CLB will has the lookup tables, multiplexers called MUX, and flip-flops. Now here this lookup table can be used to implement any logic. Later I will tell you how this lookup table can be used for various logics. Now each programmable logic block, here programmable logic block indicates that the lookup table block, can be programmed individually to perform unique operation. That means since one CLB has multiple lookup tables, each lookup table can be used for programming the unique function. Now here flip-flops can be triggered either on positive edge or negative edge. Here flip-flops are used for connecting. Either they use as the storage element or buffers, okay, to pass the information. Now multiplexers allows the selection of the logic from lookup table or external input. Now here in this diagram we could see multiplexer is connected, one input of the multiplexer is connected to the lookup table, another is connected to the external pin. Now here you can use mux for selection of the logic either from the lookup table or external pin, or here there might be logic from another lookup table also. Okay, here in the 2:1 multiplexer, one end can be connected to one lookup table, another end can be connected to another lookup table, and in the case input, one input is connected to one lookup table, another input is connected to another lookup table also. But here in this diagram, the second input is connected to the external pins. Now if you want to derive the logic from two different lookup tables, we can use this multiplexer to choose the logic from any one of the lookup table, and then that can be passed to the output through the flip-flops. Here in this case, flip-flops acts as the buffers or storage elements. Now this is what the internal view of the configurable logic block. Now let us look at this slide. Here there is single lookup table. You could see the same lookup table can be used as logic to implement two different systems. Now you could see here first system is having simple NAND gate, that is y equal to x1 NAND x2. That is what the lookup table indicates. That lookup table derive the logic of NAND gate. Now the same lookup table can be used for deriving multi NAND gate circuit. Now you could see here same lookup table, but at a time that particular lookup table can act as either single NAND logic or multi NAND logic. That depends on the lookup table content. Now in this diagram you could see same lookup table is using same lookup table is acting as one NAND logic in first case. After that the same lookup table can be used for multi NAND logic also. But at a time one logic can be implemented. Both logics cannot be implemented at a time in a single lookup table. Keep that in mind. One lookup table can represents only one logic at a time, but that can be reconfigured. Now here the word we are hearing, the reconfiguring or programming. Here in the field programmable gate array, that reconfigure or programming will happen by programming the lookup tables. Now content of the lookup table can be changed in order to change the logic of that particular CLB. So this is one example where lookup tables play the major role in configuring the system logic. Now since here there are 4 inputs, this lookup table can implement any function of 4 inputs. If lookup table is having 6 inputs, that can take any function of that can be used for implementing any function of 6 inputs. Now the number of inputs for the lookup table depends on the architecture of FPGA. Later on I will introduce you architectures of FPGA. Now each FPGA will have different lookup tables, but here for your understanding this lookup table inputs may vary, number of inputs may vary. Now as I said, now if you look at the FPGA, here you could see configurable logic blocks. There are multiple configurable logic blocks. Now we can use more than one configurable logic block for implementation of our design. If you use more than one configurable logic block to implement your design, then there is need of interconnecting those configurable logic blocks. Now that is what the concept of switch matrix interconnections. Now here, you see here, there is gap. Here there will be switch. So with the help of that switch, we can connect one configurable logic block with another configurable logic block. And that I am going to explain you now. Now here you could see this is one CLB. Here one more CLB will be there. Here some other CLB will be there. Okay, now if you want to interconnect this CLB with this CLB or this CLB with this CLB, we can use the switch matrix. That means the switch matrix is again having the switches like this. Okay, so here main logic is the programming the switch matrix. We can call that as programming interconnections. Programming interconnections. That means programming the switch matrix indicates the interconnection of the CLBs. Now that can be done in three ways. That is what we have seen. In CPLD, there is only flash concept is applied, but here there is SRAM, flash, and anti-fuse. These are the three programmable interconnections can be used in field programmable gate arrays. And this programmable interconnection also vary from architecture to architecture. Some of the FPGAs will have the SRAM programmable interconnection, some may have anti-fuse, but some may have both or three functions. That depends on the family of FPGA. There are n number of FPGAs. Based on the family what we are choosing, there will be programming interconnection logic. But here in general, we can say that field programmable gate array use these three programmable interconnections, that is SRAM, flash, and an anti-fuse. Now this is what the SRAM concept. Here we can use the pass transistor. Okay, we can use pass transistor. I hope you studied the pass transistor in our BTech. Okay. Now pass transistor simply pass the input from one end to another. Sorry, not input, signal from one end to another end, where gate acts as the switching. Okay. Here that the gate is connected to the SRAM. So that interconnection through the pass transistor will be controlled by SRAM. Now this is another technology, as I said, anti-fuse. Okay, we can use the anti-fuse and also FET transistors for programming. Okay, now no need to concentrate much on this. Why? Because this was taken care by the manufacturing units. But we have to understand what kind of the programmable interconnections are used in that particular FPGA architecture, what we will be using in the field. Now from this is the comparison of various programming technologies, that is interconnection programming technologies, where mostly we can use SRAM and flash. Now look at the parallel computing. Now as I said, field programmable gate array supports the parallel computing. That is the major advantage of field programmable. Okay. Here you could see the logic kept in the form of algorithm. D equal to A minus B, E equal to C plus F, G equal to D by E. Now you could see at the left hand side, there is software solution written. At the right hand side, you can see hardware solution. HW indicates hardware, SW indicates software. Software in this case, if we use the general purpose processor, I hope general purpose processor is microprocessor, what you studied in our BTech. Okay, if you use, there is need of using the instructions, okay, in order to perform the operations. Now let us look at this set of instructions. Loading A, first we need to load A, next load B, then perform the subtract. After loading A and B, then only we can perform the subtraction and then store the D, right? And again load C, F, then perform the addition. After that, we can do the operation on both D and E, that is division operation, and finally we can store the data in G. Now here it requires the 12 clock cycles, and also the microprocessor is having only one core, to process it. But nowadays microprocessors are coming with multi-cores, but in general microprocessors are sequential circuits where only one instruction can be executed at a time. So here one by one can be executed. That's why it takes 12 clock cycles. But wherein if you use the FPGAs, since in FPGA you could see there are many parallel configurable logic blocks. Here I can use one configurable logic block for one operation, another configurable logic block for another operation, and then I can use third configurable logic block for third operation. So here if you look at this, first D and E equations are independent to each other. Why? Because D is depends on A and B, E is depends on C and F. Okay, these two are independent to each other. D and E both are independent to each other, so that we can use two configurable logic blocks to perform the operation at a time. That means one logic block performs the subtraction operation, at the same time another configurable logic block performs the addition operation. Now after this, both can be done by using, that is division operation can be done by using another. But here you cannot use the parallel processing. Why? Because now the equation G depends on D and E. Until unless D and E are computed, you cannot get the value G. That's why there is another level is required. That's why here you can see only 2 clock cycles are required. Now first clock cycles that performs the addition and the subtraction operations parallelly. Then for the second clock cycle that performs the division operation. Here only 2 clock cycles is enough. But wherein the general purpose microprocessor requires 12 clock cycles. Now from this we can understand how FPGA minimize the execution time of the application. That is how the FPGA has become popular, because of its parallel computing. Now this minimization of number of clock cycles is possible only when parallel processing is available, and now these FPGAs are having capability of doing or executing the applications parallelly. But here we need to remember one thing: in order to support the parallel processing, there should be equations which are independent to each other. Here you could see D and E both are independent to each other. Then only both equations are computed parallelly. If both are dependent to each other, there is no possibility. Like you could see E and G are dependent to each other. Until unless E is computed, G cannot be done. G cannot be computed. That's why G have to wait for E. I hope you understood when parallel computing is possible in FPGAs. FPGAs are having the parallel processing capability and also reconfigurable capability. These two made the FPGA as superpower for most of the real-time applications. Now let us move to next. Now till now we have understood that how effectively we can use FPGAs. Now from the previous slides it is clear that FPGAs are efficient and also requirement of the day because of its parallel processing capability and also reconfigurable capability. Now here let us see how to work with FPGA. That means if you want to use FPGA for developing digital systems or if you want to use FPGA to implement real-time application, now one must follow these sequence of steps. Now here this slide clearly states that the programming and system design sequence what we need to follow for FPGA. Now initially we will write HDL code. We can call that as RTL design. RTL indicates that register transfer level. Okay, here we can describe the RTL by using HDL languages. Here we can use Verilog HDL or VHDL. These are the two widely used HDL languages, right? These HDL languages are used for describing the system behavior. Now, initially we have to write HDL code, and then we verify the behavior of the system through a logic verification tool. There is a separate tool is available for logic verification, and then after writing HDL code, we go for logic verification, where we can verify the behavior of the system. If the behavior of the system is perfectly fine, and then we go for the synthesis. Otherwise, we'll go back to the RTL design, where we do rewrite the HDL code, and then again we verify the behavior in the stage of logic verification. After successful completion of the logic verification and found the behavior is perfectly working, and then we go for synthesis, where synthesis converts the HDL code what you have written into gate level netlist. That is what synthesis generates technology mapped gate level netlist. Gate level netlist indicates that the interconnection of gates, where before the synthesis, whatever HDL code you have written, that will be having only English letters or some constructs of HDL in the form of English. But now after the synthesis, you could see now that English letters are converted into the gate level netlist, where gates, logic gates are interconnected together to perform the specific operation. And then we place and route the logic gates onto the configure area of FPGA. That is what we can call place and routing. Placing the netlist onto the configurable part of FPGA architecture will happen at place and route stage, and then we verify the timing with the help of RTA analysis. Now, after verification of the timings, we generate the bit file. After generating the bit file, we configure the field programmable gate array with the help of that bit file. Now, these are the sequence of steps what one must follow in order to implement any digital system on FPGA, starting from RTL code to download the bit file onto the memory of FPGA. Why here memory? As I said previously, okay, we can store the bit file onto the memory, that is SRAM, and that SRAM will reconfigure the lookup table and interconnection between the configurable logic blocks, so that the FPGA acts as the system what we have developed for. Now, these are the sequence of steps what one must follow to design digital systems on field programmable gate arrays. Anyway, after this webinar, we will be having 3 days virtual training on field programmable gate arrays, where we will be developing the digital systems on FPGA. During the training process, I will give you a hands-on experience for all these stages: how to write the HDL code, and then how to verify the HDL code, then how to convert the HDL code to the gate level netlist, and how do we place the netlist onto the configure part of the FPGA, and then how do we verify the static timing analysis of the design, and then how to generate the bit file. Finally, how we can download the bit file generated onto the field programmable gate array for testing its functionality. Now, these are the sequence of steps what you will be learning during that training session, where I will introduce the tool. Okay, we will be working on the tool in order to implement the systems on field programmable gate array. Now, as of now, I hope you understand that what are the sequence of steps what we need to follow in order to design any digital system on FPGA or implement any digital system on FPGA. Now, let me introduce the commercial tools are available for working with programmable logic devices. Here, especially, I can say programmable logic devices are FPGAs. Means in nowadays, widely used programmable logic devices FPGA, and I hope most of your colleges also having the programmable logic devices. Now, here simulators are Model Sim from the Mentor Graphics and Active HDL from Aldec. Similarly, synthesis tools are available from Synopsys as well, Mental Graphics, and also Xilinx. Now, if you look at the vendor tools, now here you can see the simulators and the synthesis tools are available from the vendors also, but vendors are having the complete flow for the FPGAs, flow for the FPGAs, whereas Mental Graphics and Synopsys companies are released tools for individual operations, out of which I can say for the simulator we can use the model sim effectively for the from the Mental Graphics. From the Synopsys we use the tool Simplify Pro for the synthesis, and also design compiler is available from the Synopsys, that also can be used for the synthesis. Similarly, Mental Graphics also having the separate synthesis tool for digital system designs. But here look at the vendor tools. Vendor tools are somewhat specially designed for field programmable gate arrays. Whatever the simulators and the synthesis tools we have seen at the first, these all are not specially designed for field programmable gate arrays. Those are tools designed to work with HDLs, and convert the HDL language into the gate level netlist. The same method can be used for the development of the application specific integrated circuits also. But here the vendor tools are specially developed for working with field programmable gate arrays, out of which the Xilinx and Altera, these are the topmost vendors who release the tool flow perfectly for the FPGAs. But here whatever Xilinx released the tool flow, that is Xilinx IS and Vivado, those tool flows will work only with Xilinx FPGAs. Similarly, Altera tool flow will work with Altera FPGAs. Now, if you want to use the Altera board for Xilinx, then there is a need of installing the add-ons. Anyway, we'll understand what are the add-ons one must install to work with various FPGAs, that I will be explaining to you during the hands-on sessions. But here clearly understand that at recently popular vendor tools are Xilinx, Vivado and Altera. Now these are the popular tools what are widely used in the market, out of which we will be using Xilinx Vivado is the vendor tool for the 3 days training program, which is scheduled on 10, 11, 12 of this month. Now let us move to the next. As I said, the commercial FPGAs are mostly available from these two companies, Xilinx and Altera. Now from the Xilinx, Spatron 3 and Spatron 6, these two are old devices, but nowadays those devices are not coming. But nowadays widely used devices are Vertex, Artix, Kintex and Zink. These are the devices which are running in the market nowadays, and we have the access of purchasing all these devices also. If your college is having you are ready to work with your devices, but if your college is not having these devices, at MLR Institute of Technology we have purchased these devices: Artix 7, Kintex 7, Vertex 7 and Zink. These are the devices what we have at MLR Institute of Technology, and you are welcome to come up and work with these devices at MLR Institute of Technology after this lockdown ends. Now from the Altera there are FPGAs available, but these all are not available in most of the academic institutions, because most of the academic institutions always go for Xilinx, but some of the IITs, NITs and some DRDO laboratories are having these Altera FPGAs. Now this is another company, but this is not so popular, okay, which is releasing the FPGAs. Now let us look at the Xilinx device family. Now as I said, Xilinx is the one of the leading company which manufactures the field programmable gate arrays along with the Altera. And since I have the work experience with all these devices, and I would like to project the features of these field programmable gate arrays, and I hope most of the academic institutions also having the Xilinx FPGA device only. Now Spotron 6, as I said, this is already withdrawn from the market, but that you could see here what technology is used in that particular field programmable gate array, and a number of CLBs. As I said, FPGA having major functional block is configurable logic block, and here you could see how many number of CLBs are available in each FPGA, and what kind of technology they have used, and what is the major application of that particular FPGA. And here you could see Spartan 6 can be used for digital system design, and we cannot use Spartan 6 for the complex systems. Again, why? Because number of logic gates. Here you could see number of CLBs are 150K. That is very less. As CPLD also having the less number of logic gates. That's why it was not used in the market. But for small applications, they are using CPLDs. Similarly, the Spartan 6 also having the less number of CLBs. That's why it is restricted to laboratory purpose only, to implement digital systems. Then coming to the Vertex 7, it is having the large number of CLBs. You could see 783K to 5540K, and this can be widely used for embedded and DSP applications. That means FPGAs can be used for wide range of applications. If you would like to implement the embedded systems, or if you want to implement DSP applications, you can use Vertex 7, and also Kintex 7. Kintex 7 also having the more number of CLBs as compared to Spartan 6, but less as compared to Vertex 7. Next, RTX. Now RTX is the device replaced by the Spartan 6. Now the Spartan 6 was withdrawn from the market. In place of Spartan, they have released the RTX 7, and this is also having the very less number of logic gates. That is starts from 6K to 218, and this can be used for again digital system designs for advanced. Why? Because I said here advanced is we can use it for the your projects, BTech projects. RTX 7 and Zinc. This is the special purpose FPGA. Now, if you look at the RTX 7, Kintex 7, Vertex 7, these are the FPGAs having only CLBs. But Zinc is the family. We can call that as SoC, system on chip family, where heterogeneous architectures are available. That indicates that Zinc is having ARM processor, ARM processor, and also FPGA. That means ARM processor and FPGA both are integrated together and given the name Zinc, where you can see the heterogeneous architectures. That is one ARM processor and FPGA, and this is what the SoC widely used for complex applications. Now, from this we can understand clearly that Vertex 7 and Zinc, these are the two FPGA devices can be used for complex applications to design the complex systems. RTX 7 and Kintex 7 can be used for moderate applications. Now, I suggest you RTX 7 for BTech projects or BTech laboratory experiments, and Kintex 7 for moderate applications, and for the research for the PhD, means whoever is working for the PhD and whoever wanted to do advanced research, they must go for the Vertex 7 or Zinc family devices. Now, this is what the overview of Xilinx devices which are available readily in the market. One can start working with those devices. Now, if these devices are available with MLR technology, and if anyone wanted to utilize those devices, you are welcome. I will support you to work with these devices, but you need to come in proper channel in the sense you can raise the request from our college. So our college will definitely accept. Why? Because that will come to my side, and I am ready to take up if you are coming to work with the FPGAs. That's not a problem. Are you able to see my screen? Anyone please unmute yourself and then let me know.
Yes, sir.
Yeah, thank you. Now we come to the end of the presentation, that is webinar. Now these are the applications where we can utilize the FEGAs effectively. These FEGAs are used for shaping the future of next generation systems through FEGAs. Now next generation in the sense 5G wireless is their embedded vision and industrial IoTs, cloud computing. Nowadays these FEGAs are used for the cloud computing, ALML, cyber security, and also for IoTs. Now here this FEGAs plays the major role in IoTs. Why? Because IoT requires parallel processing. Why? Because n number of sensors are connected to the single device, and if that single device is sequential device, that cannot run effectively. Now if that device is parallel computing device, that is FECA, then there is chance of handling all the sensors parallelly. Otherwise, now whatever devices they are using in the market, those all are sequential systems. Sequential systems in the sense they can process the data one after another. They cannot process the data serially. That's why more number of devices are used in IoT. But if you use the field programmable gate array in IoT applications, you can minimize the device cost drastically to one or two FPGA devices. Why? Because each CLB is capable of handling with one sensor. So here, if you have 1000 CLBs, there is possibility of connecting 1000 sensors at a time with FPGA. Otherwise, you need to use multiple sequential devices for the IoT. Similarly, embedded vision. Why here I written embedded vision? Now more research is happening on artificial intelligence, and artificial intelligence requires the vision. And here, since the field programmable gate array has the capability of parallel processing, now all the multimedia in the sense of image and video can be processed parallelly. Why? Because they have the pixels, and we can do operations on pixel by pixel. Working with pixel by pixel is the parallel processing. Okay, that is possible with the help of the FPGA. That's why again the FPGA has the large growth in embedded vision also, and also 5G. 5G require high speed, where this FPGAs nowadays has the capability of running the applications at a high speed and also flexible enough. Now these are the applications what we can work on using the FPGAs. Now that is end slide. Means if you have any queries, you can raise, so I can give you the clarity on the queries. Now I hope you understood. Just before the queries, just I would like to summarize. We have seen the various programmable logic devices, out of which we found that field programmable gate array is the device suitable for current requirements because of the parallel processing and reconfigurable capability, and that leads to work with advanced applications. As I said, 5G, embedded vision, IoT. Okay, these are the recent advancements happening now that FPGA enable us to work with all these things. And if you want to work with field programmable gate array, we need to know the flow, which flow we need to follow to develop any digital system or to develop application on FPGA. And I have given you the overview of the flow, what we have to follow to develop any application or digital system on FPGA. Now finally, I have shown you various FPGA devices available in the market, which can be utilized by you for your research and do your research. Now thank you. With this, I am closing my presentation and open for the queries. Hello, am I audible? Hello.
Sir, Sir, one question from the participant, sir.
Yeah, please, ma'am.
What's the current running technology in IC design?
Technology in this sense means they wanted to know the nanometer technology.
Yes, sir.
Yeah, now you coming to the FEGS. Okay, we are means there are Vertex 7 and Jink families are running, and now they are working on 7 nanometer and 4 nanometer technologies. Now, but these are the FEGA device, whatever I have projected here, these all are old technologies.
One more question, sir. Difference between microcontroller
Yeah.
and FPGA.
Yeah, microcontroller executes the application by writing the sequence of instructions. That means if you want to execute any application, you need to write the program, wherein there is no need of writing the program. Here we can develop the application. That indicates that microprocessor is the device already developed, and we can use that microcontroller using the program or instructions available. But here in FEGA, whatever application you wanted to work with, that application can be developed directly by using HDL language. For example, if you want to perform the addition operation, you have to write the instruction, okay, move a comma b, or a equal to 2, b equal to 3, and c equal to a plus b. Then only microcontroller can do that operation. But here in FEGA, we don't write the program. Here we write the program for the addition, that is half adder, and then FEGA can configure as the half adder and work it. So here most of the time will be reduced in the FEGS as compared to the microcontroller. In microcontroller, there is a need of running the operating system or instruction, but here the application is configured so that directly that takes the input. There is no intermediate channels in the FEGS. In summary, I could say that microcontroller is readily available device to work with the application by writing the programs. FEGA also readily available device to work with applications by configuring the applications on FEGA. I hope you understood the difference. There we need to write the program. Here you have to structure the application. After structuring the application, directly we can give the inputs to the architecture, whatever application you have developed. But here in microcontroller, you have to give the input to the fixed channel, and that channel will take that input to the microcontroller for the computation. I hope you understood. And compared to speed also, microcontroller is having very less speed, okay, in terms of mega. But here you can get a higher speed as compared to the microcontroller. Any more queries, ma'am? Now, if they have attended, in the future, we have planned a 3 days training program. There, they can understand clearly, okay, what is the difference between the microcontroller and FEGA, and how FEGA is efficient as compared to the microcontroller.
Thank you, sir.
Yeah, thank you, ma'am. Any queries, please?
All the participants are requested to fill the feedback to get the certificate. I posted the feedback form in the chat box.
Any queries from the faculty side and the student side? Now, if I don't get the queries, I can understand that you have understood everything clearly. Otherwise, you understand nothing.
Sir, one more question. Can
Yeah.
you explain FinFET technology?
What, ma'am?
From the participants, sir. Can you explain FinFET technology?
Yeah.
FinFET.
FinFET. FinFET.
FinFET.
FinFET. Actually, I could say clearly. Okay, that is out of my topic. FinFET. Actually, I will be working on more FEGS. If you have the queries related to the FEGS, please ask me. And now means this particular webinar is on PLDs. So if you want to know more about that FinFET, we can meet me later. Okay, I can explain.
Sir, address the students or participants or faculty like regarding the software installation session, how it is going to take place.
Yeah. Now, if you don't have any queries, I will
Sir,
proceed
one
with.
more question. What is the
Yeah.
present research area in VLSI?
Present research area is moving towards the nanotechnology. Nanotechnology in the sense that device level, that is one. And if you ask me, research area in the FEGA domain. Now, in the FEGS, more research is happening in communication protocols. Now, here most of the time is getting wasted to communicate with the configurable logic blocks. Okay. Now, here in FEGS, now technology is moving towards heterogeneity. As I said, there is Jink family. In Jink family, there is ARM processor and FPGA. FPGA can be used for configuring multiple function blocks. Now, there should be communication protocols to interconnect these all function blocks. Now, most research is happening on the communication protocols. We can say simply on-chip communication protocols. Why? Because this communication between the function blocks is the challenge, where most of the time is getting wasted. Computation takes very fast, but carrying the data from one function block to another function block only kill the time. Now, that is the emerging area on FECS.
Sir, most of them are asking for PPT.
Yeah, I will share the PPT with you. I will share the PPT with you. Means I can send this PPT to Aruna ma'am, and you can collect it from them. And also I can upload this PPT to the Google Classroom. Okay, we have created the Google Classroom where you will be getting the assignments for the training program. Okay, where I can upload this PPT, you can download from there directly. That is also option available for us.
Sir, one more question from the participants. What is the difference between the front end and back end tools?
Front end and back end tools. Now here, as I said, there are 5 abstraction levels. Now, out of 5 abstraction levels, start from the gate abstraction level to system abstraction level. These are the 3 abstraction levels comes under the front end. Front end in the case, we can write the HDL program, then convert into the gates, then convert into the modules, then interconnect the modules to develop the complete system. Okay, that is the front end. Back end in the sense, not writing the code, designing the transistors, more efficient transistors, and then interconnecting the transistors to develop the gates, logic gates. Now, if logic gates are efficient and modules and system also efficient, right? Working at the transistor level and circuit level comes under the back end. Working with HDL programming, and then gate level netlist, completely interconnection of the systems comes under the front end. Simply I can say semi-custom is the front end, full custom is the back end. Full custom, that is remaining 2 steps, is the back end. Am I clear?
Sir, one more query is there, like uh, mm, explain about deep learning processing
Here.
unit with CNN.
Deep learning.
Deep learning processing unit with
Yeah.
CNN. I think it is.
See here, means we cannot explain whatever the concept you have explained in detail, but I will give you the concept how to approach the deep learning by using the FAGS. Now, as I said, designing half adder is simple. Now, if you interconnect the half adders, gives you full adder. That is also simple. If you interconnect the full adders, that gives you higher bit adder. Okay, like that. Deep learning requires interconnection of many small blocks. Okay, same you follow the same mechanism how we are following to develop the arithmetic logic unit. Same to achieve the deep learning also by using the FACS. Deep learning in the sense we need to train the system. Training system requires integration of many small blocks, and that is possible here also, but you need to work in depth. Then definitely achieving the deep learning through FAGS is possible. That is what the emerging research area. I couldn't say another one. Okay. Now, as I said here, I hope you could see the screen. Okay.
I think last question, sir. What are the basic requisites we require to write a program in FPGA?
If you know the C language, that is enough to understand the Verilog HDL. Why? Because most of the Verilog HDL constructs are derived from the C language. I hope as the engineering student, you might have studied in the first year itself the C language. If you have the basic knowledge about the C language, then writing the HDL is very easy. Anyway, in the lab sessions, we will explain you clearly how to start with. Okay. Is that clear? Any more queries?
No, sir.
Yeah, means to kickstart with the lab sessions, okay, scheduled from 10 to 12. There is a link shared here in the chat box. You can download that software and install the software in our laptop. To work with the Verilog HDL, you need the software that is Xilinx Vivado, and the link is shared. That is around 6 GB file. Download that software and install in our laptop. And if you face any problem during the installation, please approach the faculty, Madam Aruna and Indira Priyadarshini. These two will help you in installing the software. Now, link is shared here. If you would like to download from that link, you can download. Otherwise, you can go to the Xilinx website. Directly from there, you can download the latest version. But the thing is that latest version is more than 25 GB. And that wastes most of our time. That's why my suggestion is download the software, whatever we are sharing with, and install that software in our laptop. To attend the practical sessions, the computer is must. If you don't have the computer, you cannot understand anything. Here, every day 2 hours only we are taking. Today there is more my talk. Okay, means I was keep on talking, but during the lab sessions, you have to work parallelly. Because of that is hands-on session. Here I will give you the basics of Verilog HDL and ask you to practice that on our laptop. During the interaction sessions, I will explain you basic concepts and some small programs, and I will give you some more assignments to work with in offline. And also I will give you the sufficient material to complete those assignments at our home. Any queries?
Sir, no queries, I think so.
Sir, last question. One question.
Thank
one
you.
question.
Yeah, please.
Sir, how to apply timing constraints, if possible, in the coming schedule, coming classes? Could you please take that?
Yeah, sure. Means there is a possibility of giving the timing constraints.
Because what I think is, okay, we write a HDL code and okay, we simulate it and we synthesize it and we generate a bit file. That's okay for smaller designs. But if you take a bit complex design, I guess without timing constraints applying and simulating it, ensuring that result is coming, we cannot go to the configuration of the device. So
Yes,
that's
yes.
the reason why I'm asking you. That will be a great added advantage through this webinar sessions.
Definitely. On the third day of our lab sessions, we will be introducing the sequential circuits, and during that sequential circuit implementations, I will explain you the concept, how to apply the timing
Thank you so
constraints.
much. Thank you so much.
Thank you. If you want to apply the timing constraints, there should be a clock, and that clock will be invoked only if we use sequential circuits.
Yes, yes.
Okay, that's why on last day session we'll do that.
Thank you.
Thank you. Yeah, I hope no queries. Is there any queries? Please let me know.
Sir,
Yeah.
good afternoon, sir. So when we are downloading the software, it is asking us to select an edition, like Vivado Web Tab or Design Edition or System Edition or Navigator. Which one should be downloaded?
Are you downloading from the Xilinx website directly?
Yes, sir.
Yeah, means you can download the system edition.
Okay.
My suggestion is download the software whatever your madam shared with you. Why? Because that online edition is having more.
No, sir. Like ma'am shared a link yesterday. From the same link, I'm downloading it. It is asking for the edition to be selected, like Design Edition, System Edition, or Navigator.
What ma'am shared? She shared the Xilinx link or Google Drive link?
Google Drive
In
link.
the Google Drive link, it may not ask. Google Drive link directly it can be downloaded. After downloading, while installation it will ask you. While installation you can select System Edition.
Okay. Yes, sir. During installation only it is asking me.
Yeah. During installation it will ask you. You can select the System Edition and then proceed. At the end it will ask you the license wizard. Okay, whenever license comes, then you can select Webpack. Okay. While installation you can select the System Edition. For the license you can select the Webpack, so that will direct you to the Xilinx website to register and then download the license. After downloading the license, you can integrate that license. Anyway, means before starting the session I will explain you how to up the license for the Xilinx Vivado. And meanwhile you can approach Madam Aruna and Madam Priyadarshini. They will help you.
Okay. Thank you, sir.
Yeah. Now my humble request is get ready with the laptop and software installed in our laptop to kickstart the lab sessions. Why? Because there are 3 more days. Okay. I hope this 3 days is enough to download the software and install in our laptop. Otherwise we have to waste the time during the session. Okay. Why? Because we have limited sessions. That is every day 2 hours only. Within 2 hours, let us utilize the time effectively for learning the concepts instead of wasting the time on in software installations and all other stuff. Okay, that is my humble request. download the software and install before starting the lab sessions.
Sir, there is a small announcement for MEC students. After the vote of thanks, stay there in the meeting. HOD sir and Sushant Babu sir will address regarding the microwave lab. Thank you. And regarding the software link, if anyone is denying the access, I'll share again, once again, with the software link to download from the drive. Okay. I try to fill the feedback form to get the certificates.
Okay. At this point, please tell me, ma'am.
Nothing, sir, nothing.
Yeah. At this point, I thank Dr. Srinivas Rao Garu, head of the department, and also Professor Aruna and Professor Indra Priyadarshini for inviting me for this webinar. And I hope we can enjoy the lab sessions also with the same energy. Thank you very much for inviting me as the speaker for this webinar. Thank you. Over to you, Aruna.
Sir, I like to propose vote of thanks. Myself, B. Indira Priyadarshini, Assistant Professor, EC Department. Good afternoon to the respected and distinguished speaker, Mr. Mahendra, HOD, Dr. Sushant Babu sir, and my dear participants. I consider it a great privilege to propose vote of thanks to all the dignitaries who have witnessed it a memorable and successful event. I express my deep gratitude to our respected speaker, Dr. Mahendra, for his enlightened lecture on programmable devices and architectures for the benefits of the participants. I would also like to thank the management, Principal Matrusri Engineering College, Head of the Department ECE, for giving us the moral support to conduct the webinar. Finally, the wonderful participants who have turned up in great number, not only from our college and also from other colleges. We thank you so much for your participants. Thank you. Thank you, one and all.
Thank you, madam.
Thank you, sir. I request all the MECS students stay for 10 minutes. HOD and Sushant Babu sir will address you. Thank you, sir. Thank you very much.
మ్యామ్ నూకల సార్ ఉన్నారా?
ఏమో చూడలేదు, చూస్తాను ఒక్క నిమిషం.
చెప్పమన్నారు కదా.
కోటేశ్వర సార్ని రూమ్ లోకి అలౌ చేయబ్బా. కోటి సార్ రిక్వెస్ట్ యాక్సెప్ట్ చేస్తలేవంట, ఒకసారి చూడు.
నాకేం రిక్వెస్ట్ రావట్లేదు.
మళ్ళీ చెప్తాను నేను సార్కి.
ఒకసారి మళ్ళీ నాకేం రాలేదు రిక్వెస్ట్.
నేను మీటింగ్ లో ఉన్నా.
అదే మైక్రోవేవ్ ల్యాబ్ గురించి చెప్తా అన్నారు కదా. మ్యామ్ నో ఫైల్ ఇస్ ప్రెజెంట్ ఇన్ గూగుల్ డ్రైవ్ లింక్. అరే అందరికి వస్తే వీళ్ళకి ఎందుకు రావట్లేదు మేడం?
ఎవరికి రావట్లేదు?
చంద్రశేఖర్, ఇఫ్ యూ గాట్ ద మెయిల్స్ ఫ్రమ్ ద మెయిల్స్ మ్యామ్, గూగుల్ డ్రైవ్ లో రెస్ట్రిక్టెడ్ నుండి
యాక్సెస్ ఇవ్వు. నీ వాయిస్ రావట్లే అరుణ. Students, please stay in the room. Don't leave. Sir, is it audible?
Yes, madam. It is
Madam,
audible.
problem na daggara.
No. It is audible for you.
Okay. సార్ ఒకసారి శ్రీనివాసరావు సార్ కాల్ చేయండి సార్ అయిపోయింది.
Okay, madam.
అయ్యాను చూడండి. అరుణ మేడం, హలో.
హలో సార్.
Yes.
వినబడుతుంది సార్.
ఈజ్ ఇట్ ఓవర్?
Yes sir. If they have the doubts regarding the software,
ఓకే,
after you, like, we will continue sir.
మీది అయిపోయిన తర్వాత తర్వాత మాకు హ్యాండ్ ఓవర్ చేయండి, అది నేను చెప్పేది. వాళ్ళని ఉండమని చెప్పండి స్టూడెంట్స్ని.
ఓకే సార్, ఒకసారి అడిగేస్తాము ఏమన్నా సాఫ్ట్వేర్ లో డౌట్స్ ఉన్నాయి అంటే. చాలా మందికి ఫోల్డర్ ఎంటీ అని వచ్చింది అని అడుగుతున్నారు. మళ్ళీ ఒకసారి రీసెండ్ చేస్తాను అన్నాను, అదే ఒక్కసారి అనౌన్స్ చేసి
మీరు
All
ఓట్
the-
ఆఫ్ థ్యాంక్స్ చెప్పేసిన తర్వాత మాకు హ్యాండ్ ఓవర్ చేయండి, ముందు వద్దు. అది మంచి పద్ధతి కాదు. అది నేను చెప్పేది.
ఓట్ ఆఫ్ థ్యాంక్స్ అయిపోయింది సార్. సార్ కూడా డిస్కనెక్ట్ అయిపోయారు స్పీకర్.
వెళ్ళిపోయారా? ఓకే,
ఓన్లీ మన స్టూడెంట్సే ఉన్నారు.
ఓకే. ఆయన ఉన్నారో ఏంటో నేను వెయిట్ చేస్తున్నాను. సరే
లేదు.
సరే, సుశాంత్ బాబు సార్ వచ్చారా? కోటేశ్వరరావు, నాగరాజు
కోటేశ్వరరావు సార్ వచ్చినట్టున్నారు. నాగరాజ్ సార్ ఉన్నారు. సుశాంత్ బాబు సార్
Sir, I am in online only.
Okay, students are there, I think. Okay. Good evening, everybody. This is one of the important solution we found out for your microwave engineering lab, not only, but also for your project work final year. Please hear carefully, and we will circulate this poster. This is in the context of HFSS software using, you have to do microwave engineering lab during the situation outside. We cannot go to the college. That is the reason behind IEEE USA is recommending one training program for across India. So 3,000 odd research scholars, professors joined in this training program, including me. So this poster and everything we will circulate, and I will project after 5 minutes. 1 minute. This is the poster what they send. Is it visible? Hello?
Yes sir.
This is the ANSYS USA and IEEE Antenna APS Society, MTT Society, and IEEE Bangalore and NTUPL, who supplied us HFS software. They are organizing this course. This I will magnify, and IEEE student members 25% discount is there. Actual fees is 2350. 2,350 for 1 month training. This is evening 6 p.m. to 8 p.m. During this 31 working days, they will give you training starting from electromagnetic field theory to advanced antenna aircraft design, like this. So antenna design, EM field theory, time harmonic fields, rectangular waveguide design, magic T design, and everything here given. I will magnify this. You can see the fundamentals of electromagnetics and application of curl divergence gradient coordinate system. Why? Because this is 3D. That is why this one they will discuss 12th August 6 p.m. to 8 p.m. And next one is the fundamentals of time varying fields, electrostatic EM field theory. Complete 2 hours. They will simulate the entire thing and they will show you. Next, electromagnetic wave propagation and its applications. 18th August. That is the 12th, 14th. After covering this, they will give you some assignments how to solve using HFSS. And all these 31 days, they will give you free of cost original licensed version downloadable link. You can practice your waveguides also during the meantime. Next one is electromagnetic wave application and its applications. 18th August, 6 p.m. to 8 p.m. Microwave components and its separate 21st. So yesterday our speaker already projected. How far you learn, I do not know, but this is a golden opportunity to you to navigate yourself at your home, evening 6 p.m. to 8 p.m. daily, starting from 12th August and so on. So because of magnifying this, it is not visible completely. I will project this 1 minute. One more thing is there. Where is that image document? This one, no, 1 minute. Here somewhere. This one only. I will open in the mail and I will show you. Anyway, the issue here is this. Okay. Is it visible? Hello, is it visible? 1 minute.
No, sir.
1 minute, 1 minute. Where is this? And this is that one here. No, this. 1 minute. See, the link is disconnecting automatically. Where is this yesterday sent you? Right? Hello? Is it visible?
No, sir.
No, sir.
Now?
No, sir.
It is not here. Now?
Now it's opening, sir.
So these all are the topics they want here. See, they have projected it is actually for 30 days 6,850, whereas for our academic institutions and because we have procured 2,350 per candidate. If you are IEEE member, 25% discount. If more than 40 people are